Okay, assume Gedanken conditions exist. Do we all remember Gedanken conditions? Just a thought conditions, right? Don't pick holes in it. That's what Gedanken means. Okay, assume Gedanken conditions exist in this example. A stationary observer on Earth sees a very fast car passing by, travelling at 2.5 times 10 to the 8 meters per second. In the car is a clock on which the stationary observer sees 3 seconds pass. Consider calculate how many seconds pass by the stationary observer's clock during this observation. Use C equals 3 times 10 to the 8 meters per second. Okay, so let's draw a diagram. There's our stationary observer. The stationary observer has a clock. Here is our car. Oh, that's not a car, that's a car. This car is travelling at 2.5 times 10 to the 8 meters per second. Okay, very fast car. And in the car is another clock. Okay, so that's what we're saying here. The car has a clock, the observer has a clock. Okay, and we want to know, so this clock ticks over 3 seconds. Okay, so we want to know the time our observer sees. Okay, so first of all, we need to work out our Lorentz factor. So our Lorentz factor, 1 over square root of 1 minus v squared on c squared. Okay, so v squared is 2.5 times 10 to the 8. So we can do 1 over square root of 1 minus 2.5 times 10 to the 8 squared on 3 times 10 to the 8 squared. Okay. Now, if you work that out, my calculator's gone missing. I think that's about 1.8 if you work it out. Yeah, you happy with 1.8? Did I hear an mm-hmm? All right, that's good. It's about 1.8. Have we got more decimal points than 1.8? Oh, okay, so very close to 1.8. Okay, so if you calculate that, now if you don't get roughly 1.8 to a decimal rounding, you've gone wrong somewhere. So we get a Lorentz factor of 1.8. Now remember that our time dilation equation is that. Now in this case, our proper time, remember your proper time is the one where if you are in that same frame of reference as whatever's measuring the time. So in this case, our proper time is in the car. We've got 3 seconds of proper time. Okay? So if you were in the car, you would observe 3 seconds going past. So therefore, your relativistic time, the dilated time, is what the observer is going to see. Okay, because the observer is not in the same frame of reference as whatever's measured the time. Okay? These can be a little bit confusing. It's easy to mix up your time and your proper time. Okay, but just remember, if your observer is not in the same frame of reference as whatever's measuring the time, then that is not proper time. Okay, proper time is whatever's measuring the time. And so if we work this out, our proper time is 3, our Lorentz factor is 1.8, and we'll get 5.4 something. 5.4? 5.4 seconds. Okay, so we have an observer watching a very fast car go past. He sees 3 seconds tick over on the car's clock. When he looks at his clock, 5.4 seconds have gone past. Okay, that is time dilation. Now, one other thing I'll tell you is proper time is the smallest that time can be. All right, if you work this out backwards, if you say put proper time there, you would see that time wouldn't dilate, it would shrink. Okay? The smallest amount of time is what you observe on your watch. That's as fast as time, sorry, that's as slow as time can go. Okay?